The function e to the x is known as the indestructible function. And the reason is that when you take the derivative of e to the x, it's the only function that has the property that its derivative is equal to just the same thing that you started with. Of course, it's also true of any constant multiple, but it's the same general form. So basically, uniquely for the exponential function, when you take the derivative of e to the x, you just get e to the x back. Let's see why this is true. Well, let's let f of x equal e to the x, and let's compute f prime of x. Well, f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. This is supposed to be minus, so I'll make it a little bit more obvious. Minus f of x over h. Okay, so let's plug in x plus h for x. So f of x plus h is just e to the x plus h. So we get e to the x plus h, and then minus f of x is just minus e to the x all over h. Well, note that e to the x plus h is just e to the x times e to the h. So we have a common factor of e to the x on both terms in our numerator. So this is the same. So recall that e to the x plus h is equal to e to the x times e to the h. Basic algebra rules. So this is equal to the limit as h goes to 0 of e to the x, e to the h minus e to the x all over h. Now I have a common factor of e to the x, which I can basically group together and pull out. So it's equal to the limit as h goes to 0 of e to the x times e to the h minus 1 over h. Now x, with respect to the limit as h goes to 0, it treats x as a constant. We're basically at a fixed value of x. We have x locked. We take the limit as h goes to 0 in order to determine what the derivative is at that value of x. And then after we take the limit as h goes to 0, that's when x is free to move around and this becomes a function of x. So for the purpose of the limit, though, as h goes to 0, x is a frozen constant. So we can pull this e to the x out of the limit just like we can pull a constant out of the limit. So this becomes e to the x times the limit as h goes to 0 of e to the h minus 1 over h. So we just have to find the behavior of this function as h goes to 0. Now I have a plot of that function. In fact, I just Googled e to the x minus 1 over x. E to the h, I used x instead of h. And then here's the graph of the function. And we can zoom in a bit more and scroll down. Let's see what this looks like. So we can see it, and it's actually undefined at exactly at 0. But if we keep zooming in, we see that it actually approaches an output of 1. So, and there should be a hole there exactly at x is equal to 0, or in this case, h is equal to 0. But basically, when you have e to the h minus 1 over h, as h approaches 0, you're going to approach the number 1, which means that this limit as h goes to 0 is equal to 1. And you can try that, so it's going to be 1 times e to the x. Right? And you can try this for a small value of h. So for example, 0.01. So I can, on my calculator, I do 0.01, take the exponential, subtract 1, and then divide it by 0.01. I get 1.005 and then some change. So 1.005. So thus we conclude that the limit of e to the x, or the derivative of e to the x, is just e to the x. Okay, so the extended version is the derivative of e to the u of x. We just rewrite it, e to the u of x, and then we multiply it by u prime of x. So it's just like we take it like normal. We have e to the u, the derivative is e to the u. But since u is not x, we have to correct it by multiplying by the derivative of u with respect to x. So let's see an example of this. Suppose that f of x is equal to e to the 3x squared plus 7. F prime of x, we just rewrite it, e to the 3x squared plus 7, and we multiply by the derivative of the exponent, which is just 6x. So the derivative is just 6x times e to the 3x squared plus 7, just like that. Let's say we have e to the 4x to the 4 plus pi. Well, the derivative is just going to be, we rewrite it, e to the 4x to the 4 plus pi, and we multiply by the derivative of the exponent, which is 16x cubed. And it's as easy as that. Now we can use this to compute or to show that the derivative of a to the x is equal to a to the x times the ln of a. So suppose that you have an exponential function whose base is not equal to this special number, which we call e. If you have, like, say, the function 3 to the x, what's the derivative of 3 to the x? Or if you have the function 2 to the x, what's the derivative of 2 to the x? Or in general, we can just say we have a to the x, the derivative is a to the x times the ln of a. Notice that this does work if a is equal to e, because the ln of e is 1, right? So let's see why this works. Well, if we have f of x is equal to a to the x, this is the same as e to the ln of a to the x, right? Remember, e to the ln of 5 is just 5. E and ln are inverse functions, so they undo each other. E to the ln of a to the x. Now, another log rule, when you have ln of a to the x can come down out front. So this is equal to e to the x ln of a. Now let's take the derivative of it, because we know how to take the derivative of this. We rewrite it, e to the x ln of a, and then we multiply by the derivative of the exponent. But the derivative of the exponent is just ln of a, right? Because it's like saying e to the 3x, the derivative of 3x is 3. Ln of a is just some constant, so the derivative of x ln of a is just ln of a. But e to the x ln of a, we just saw, was the same as a to the x. So the derivative is a to the x times the ln of a. So an example of this, so suppose we have f of x is equal to 2 to the x, then f prime of x is equal to 2 to the x times the ln of 2. Now we can also extend this with the chain rule. If we have the derivative of a to the u of x, derivative of a to the u of x is just a to the u of x times the ln of a times u prime of x. So for example, if we have f of x is equal to, let's say 10 to the x squared. Well, the derivative, we just rewrite it, 10 to the x squared, multiply by the ln of the base, and then multiply by the derivative of the exponent, right? So the base was 10, we rewrote it, and the ln of 10 is this part right here. And then the exponent was x squared, and the derivative of the exponent was just 2x. So that's exactly how we do it. So we rewrote 10x squared, 10 to the x to the 2, multiply by the ln of the base, and then multiply by the derivative of the exponent.